Hello, how you guys going? I thought I would actually do the 2024 VCE exam finally, the one that's actually relevant to your study design. Um, yeah. So, with that being said, it's really interesting. Like the previous study design, I was just saying, went from 2017 till 2023, which I feel like is quite a long time. So anyway, photosynthesis is basically the opposite of cellular respiration. So it's an endothermic because it's basically it's using sunlight, which is its main source of energy, to produce glucose. So it's an endothermic. I don't know if it's like it's definitely a redox react. Like, so it's what, 6 CO2 plus 6 H2O. To produce C6H12O6 plus water. Like it's definitely a redox reaction, right? Because obviously that is being turned into that. That is re so carbon dioxide is reducing to form that. So there's definitely some transfer of electrons going on here. Also, the other reason why it's not a condensation reaction is there's no, production of water here. I don't know. I've never seen condensation be used in the context. The oxidation of glucose is reversible in the body. Not really. So once glucose has been broken down to produce ATP, it can't be reversed. The combustion of glucose provides less energy per gram than the combustion of hydrogen. Um, um, so here, hydrogen was so it would be so it'd be 1/180. So that's a molar mass of glucose times 2803, and it'd be 1/2 times 286. Now I'm sure there's a faster way to do this. I'm sure there's a more intuitive way of doing this, but that's the way I'm doing it. Okay. Uh 2803 divided by 180. So that's 15. That's 16 kilojoules per gram. And then 286 divided by 2, that's 143 kilojoules per gram. So provides less energy per gram than the combustion of hydrogen. That is true, which you wouldn't think so. But because the molar mass of hydrogen is so low, it actually turns out to be okay. The oxidation of glucose, no. When you turn glucose into carbon dioxide, then you are oxidizing it. Okay. The combustion of oxygen occurs during cellular respiration. No, the combustion of glucose occurs. Um, cool. If complete combustion which reactor? So, if complete combustion takes place, basically it means that ethane is completely being combusted. It's completely reacting, which means that oxygen would be in excess. Okay, and the amount of reaction in excess. Uh, this feels annoying. So we do C2H6 plus 7/2O2. Now we got 100 grams of air, and then 22% of that is oxygen. So we've got 22 grams of oxygen. Okay, so to find out how much oxygen we initially have, would be doing 22 divided by 32, which is 0.6875. So the amount of moles of oxygen we initially have is 0.6875. Then this is also Ni is zero point 0.5, right? So the amount that's going to be left, so zero point 0.5, so we've got zero point 0.5 moles of C2H6. So the amount that's of oxygen that's needed to react with that is just zero point 0.5 times 7/2. So what's 0.5 times by 3.5? It's 1.75. That's not in excess, is it? What have I done wrong? So 0.5 times 7, 2, 1.75. I've done something wrong here, definitely. So I've got 100 grams of air. So then 22% of that. So that wouldn't be 22 grams. And then 22 divided by 32 is 0.8685. If complete combustion and amount and how much of it? 0.5 moles. So the amount that's reacted. Complete combustion takes place. Okay. Let's just figure out this. So NR is 0.6875. And then so there's a one, so there's a 7/2 ratio. So I would just need two, so it's basically it'd be 2/7. So I just times by 2 divided by 7. So it'd be 0.196. Um I have so C2H6. Oh, so maybe what the entire idea of this question is that we don't assume that O2 is going to be in excess. We actually have to figure it out. And what you'll realize is that, we've got more C2H6 to start off with. So I figured out 0.6875 because 22 divided by 32. Then you just times this by 2/7 to find out how many moles of, ethane is actually required to react. And then it's just that. So it'll just be zero point 0.5 minus 0.196, I think. So 0.5 minus 0.196, and you get 0.304, which is that. That is a very sneaky question, but also it's also a new addition to the study design, so I should have been paying more closer attention to that. So here, there's a couple changes going on here. So here, we're obviously, this is in order to form that, it's probably losing electrons, so that's oxidizing. So this is probably reducing, right? So I minus is going to go from I2 plus 2E minus, right? And then H pluses, the H plus, it's still H plus in water as well. So the oxidizing agent, well, that is reducing. So it'd be, yep, that. And then the conjugate redox pair, so the oxidizing agent comes first. This is the oxidizing agent, so that. Oxidizing agent. Sorry. So the oxidizing agent we've already identified. So the reducing agent should be this. Yep, sorry. So it'd be this. Um, yeah, just to really, I think I rushed through that, but we know that this is the so this is oxidizing, so that's the reducing agent. And it says reducing agent here last, which is that. Sorry, that was a stupid mistake. Cool. When the galvanic cell is operating, the total chemical energy is increasing. So here, okay, so if you guys can see, um, oh, SN2, so here, and then here. So that's probably what's going to be happening, right? The SN4 plus is on top, so that's that, just to make sure. Yep. So total chemical energy is decreasing. So it'd be decreasing, right? Because there's a change. So we're going from chemical to electrical energy. So it'd be decreasing. And then the electrons are flowing from half, and the electrons flow to half cell A. So it's going this way, right? Because lead is oxidizing because it's lower on the data book. So it'd be C. Um, which one of the following statements? A galvanic cell is set up using inert electrodes and the following chemicals. One Okay, and an oxygen in an alkaline solution. What would be oxygen in an alkaline solution? It would most likely be something like this, wouldn't it? So it'd be oxygen, and then we've obviously got water. It'd be something like that. I'm just thinking, is there anything else that's oxygen in an alkaline solution? Don't think so. So it'd be that one. So the other reason as to why I know that is because that and that are pretty much the exact same thing, except um, it's basic in acidic environment. Okay, so it's that, and then and then this is 1.2 volts. So the other equation is 1.2 volts, which is somewhere there anyway. Okay, so so this would be going from here to there. Hydrogen gas is produced at the cathode. Well, this is what the cathode would be. And there doesn't seem to be any hydrogen gas being produced, so that's okay. The oxidizing agent, so that's being reduced, so it would be the oxidizing agent. And the reducing agent is oxygen. I don't think so. So the reducing agent is that. So that's being oxidized. Don't think so. The concentration of hydroxide ions decreases at the negative electrode. Yes, it would be, because that's being converted into that. Okay. So that would be the mass of the electrode in half cell one decreases. No, because you're using inert electrodes, which don't even participate in the reaction. So six what we see. What mass? Okay, um, so you've got 0.5 moles of electrons. There's a 2-to-1 ratio. So there's 0.25 moles of copper being produced. So we just do 0.25 times by the molar mass of copper, which I believe is 63.5, which is 15.875. This one. The use of porous electrodes increases cell efficiency, obviously, as a ratio of the amount of hydrogen supplied to the amount of electricity. Is the ratio of the amount of hydrogen supplied to the amount of electricity produced increases? The efficiency increases as the ratio of the amount of as the ratio of the amount of hydrogen to the amount of electricity produced increases, the efficiency increases. No, wouldn't we want? I don't know. This is worded very weirdly. I don't think so. Because if we're producing more hydrogen respective to the amount of electricity that's being produced. So if the ratio, so basically, I think this is the ratio, it's hydrogen to the amount of electricity. And if this ratio is increasing, that means we're giving more hydrogen. However, it, despite the hydrogen going up, the electricity isn't going up. So the ratio is decreasing, which means the efficiency is decreasing, which means neither one or two is correct. But that's weirded. That's worded very weirdly. What amount of hydroxide ions reacts with 1 mole of ethanol? So, you want to show the oxidation. So this is, I don't know if this is a good way to do it. So you want to do, so I like to show the oxidation of ethanol in an acidic electrolyte, and then I want to turn it into a basic electrolyte. So there's three H2Os, and then that's 612, so 12H plus and 12E minus. Let me just check that's right. So that's 4, 3, H2O, 6, 12. And then in order to turn it into a basic electrolyte, how many ever H pluses there are, you add 12 hydroxide ions to each side. So if I add 12 hydroxide ions and 12 H pluses, I mean, if I add 12 hydroxide ions, that will combine with the H pluses to form 12 waters, and then there'll be 12 hydroxide ions there, and there'll be 9 waters. So what amount of hydroxide ions reacts with 1 mole of ethanol? So 1 mole of ethanol, 12 moles of hydroxide ions. Cool. Bioethanol fuel is sustainable because it results in no net release of carbon dioxide into the atmosphere. No, not necessarily. So obviously when this is obviously referring to how sugarcane, they absorb carbon dioxide when growing through the process of photosynthesis. And then when bioethanol is burnt, it also produces CO2, but obviously that's offset by the CO2 that's absorbed. However, you know, the actual processing of the bioethanol fuel, breaking up the sugarcane in order to extract glucose, those are all energy intensive processes. Okay. Hydrogen peroxide can be used as an oxidizing agent in fuel cells. Um, can be used as an oxidizing agent. Um, So H2O2, if it's an oxidizing agent, then it can undergo reduction. Here it says it can. Can that not? So H2O2, and it reacts with the H pluses and the electrons. So I would say that two could be correct because it can be used as an oxidizing agent if it reduces. However, I is not correct. So I'd say two only, maybe for that. Iron is produced from iron ore using a heat and reducing agent. Okay, using hydrogen, using hydrogen as a reducing agent to produce iron is consistent with um is consistent, okay, with the concept of a so because we're using fossil fuels, this definitely wouldn't be a circular economy because it's not like we're reusing any of the stuff. So it would be a bad thing. So it'd be more a linear economy. So we're using natural resources. Yeah. Um, yeah, so we're definitely not recycling or anything. We're basically using it and disposing it, right? Because there's no alternative use for that hydrogen. Cool. Yeah, I mean, obviously, as soon as you see fossil fuels, you would not, associate fossil fuels with circular economy or the United Nations Sustainable Development Goal. The combustion reaction is considered irreversible because the forward reaction is exothermic. The product of the rate of the reaction, unlimited supply of oxygen. The rate of the reverse reaction is so slow that it can be ignored. The forward reaction is exothermic. Well, that's definitely not true because obviously there's a lot of reactions. The products are less stable than the reactants. Um, so the rate of the reverse, so you know. I'd say it's considered irreversible just because, yes, the rate of the reverse reaction, like it could be happening, but because it's so slow, it's pretty much ignored. There's such a large, release of heat energy that occurs that, even though it could be occurring, it's occurring at such a slow rate that it's pretty much borderline ignored. There's not an unlimited supply. What are we talking about? Infinite supply of oxygen? I don't know. It just seems very odd and, favoring the forward reaction. I don't know about the products being less stable than the reactants. And honestly, the products are actually more stable than the reactants now that I think about it. Because, whenever we have a lot of energy, we've absorbed a lot of energy, we're very jittery and things like that, like when we're very energetic. So these are what the reactants are like. They're very energetic, so they're much less stable than the products which are low energy, CO2 and H2O, so they're much more stable. I don't know. I don't like the unlimited supply. Adding a catalyst to the unclot will increase the energy. No, it won't change the enthalpy of the reactants. Removing the catalyst from the catalyzed reaction will increase the rate of the reaction. Nope. Um, Removing the catalyst from the catalyzed reaction will increase the activation energy. Yes. Okay. Very obvious. What reaction condition? So this is endothermic. So if we have increased pressure, then they will try and decrease the pressure, okay, by favoring the side with the least moles, right? Favoring the side with the least moles, which would be this way, Okay, so we would want low pressure. And because it's endothermic, it's okay if we have a higher temperature. Because a higher temperature, LCP will say, let's lower the temperature. Now, energy is this way. So if Le Chatelier's principle is saying, hey, let's lower the temperature, it's going to favor the reaction from going forward. So it actually consumes the energy. Or or you can think of it as it's favoring the reaction in which no energy is being produced. Homogeneous equilibriums of decomposition to form SO3 and O2. Some SO3, which is then sealed. So basically, what it's saying that basically, if you think about what is SO3, uh, so that's basically what's happening. So basically, let's say, for example, this is X. Okay, so we have some X, some SO3 that's placed in the container. This is 0, 0. And we have Y that's left with. So then the overall change would just be X minus Y. And so then this would be 2X minus Y. And then just be X minus Y. Um, the mass of the amount in moles. So this would be 2X minus Y. And that would be X minus Y in moles. The mass of SO2 is 4 times the mass of O2. I think it's just 2 times. Is it not? Okay, wait, let's have another look at this. So, which one of the following is true at all temperatures in the sealed system? Okay, homogeneous to form SO2 and O2. So, oh wait, oh wait, no, hold up. It should be X minus Y over 2. Completely done this wrong. So this should be X minus Y. This should be X minus Y over 2, right? It's because that's the same change. So mass of SO2 should be 4 times the mass of O2. Um, let's think about that. The amount in moles of SO2 and SO3 are the same. I don't know. So, um, starting off, 2 and SO3 are the same. I don't know what they mean by homogeneous, homogeneous equilibrium. Hmm. The mass of SO2 is 4 times the mass of O2. So this is X minus Y over 2. This is 32. 32, that's 64. That's 32. So it'd be 64 times X minus Y. And then that's 32 X minus Y over 2. So 64. Oh, so there's a 4-to-1 ratio. So A is correct. It's tough though. I don't know. It's very tough. Um, few drops. Okay. A few drops of sodium NaSeN are added. The equilibrium constant at T4 is lower than at T1. Yeah, probably. Um, okay. Maybe. Yeah. Looks like I mean there is more SCN. However, generally speaking, the only thing that can really change the equilibrium constant is temperature. chemical energy of the system increases between T3 and T4. The chemical energy of the system. I don't even know what that means. I don't think so. It's just the chemical energy of the system increases. The chemical energy. Maybe it's talking about the amount of stuff that's being produced. However, we're going from 2 to 1 in this situation. When we're going from T3 to T4, the SEN has increased in concentration, which means the forward reaction is being favored, and therefore we're going from two, moles of chemical species to 1 mole of chemical species. So I would say the chemical energy is decreasing. The rate of the reverse reaction was less than the rate of the forward reaction at T3. So at T3, uh, we are trying to favor the forward reaction. And so therefore, yes, the rate of the reaction would be less than the rate of the forward reaction. Both the concentrations of Fe3 plus and FeSEn are higher at T3 than at T1. So at T3 and then at T1. So the FeSEn concentration, oh no, are higher at T3. So here, the Fe3 plus, let's just take that for example, only the SEN has increased in concentration, right, guys? Um, the only thing that Fe3 plus has begun to do is now started to be consumed a bit more, right? Because now we're favoring the forward reaction. There was no initial change to the concentration. So the concentration of Fe3 plus, right? They've only shown SEN here. The concentration of Fe3 plus at T3 would actually be lower because there was no initial change to Fe3 plus. So C would be your best answer. A blister of copper. Ah, these sort of questions. Very, very interesting. Electrolysis of blister copper. So concentration of copper. Um, so basically what they're trying to do is they've got blister copper at the anode, right? And basically what they're trying to do is they're trying to have all the other metals go down to the bottom, oxidize the copper from there so that it can be plated onto pure copper. Okay. So the blister copper is used as the cathode, it's used as the anode. Solid iron falls to the bottom of the electrolysis cell, maybe. Then 99.99% pure copper product should be removed as it forms. Uh, no, it doesn't need to be. Okay. The concentration of copper 2 plus ions in the electrolyte changes during the electrolysis. Well, yeah, probably, right? Because it's being added on to the pure copper. That's probably your best answer. The solid iron falls to the bottom of the electrolysis cell. Let's see why that is wrong. So we've got silver, iron, and nickel. So we're looking at ones that would oxidize the most. Silver, iron, nickel. So we've got silver, which is all the way there. Don't even, silver, iron, nickel. Wait, silver, iron, nickel, and copper. Where's copper? Copper's here. So, in terms of what would actually oxidize, it would be your strongest reducing agents. So this would definitely oxidize. So a solid iron would not fall. Okay. The only interesting thing here is these would oxidize to form this. This would oxidize to form that, and that would oxidize to form that. So out of these three ions, the one that's most likely to actually reduce onto the copper is this because it's the strongest oxidizing agent. So solid iron would not fall, okay, because it'd actually be involved in the oxidation process. Obviously, the concentration of copper 2 plus ions would be changing. It'd be going up and down. It'd go down as it's reduced onto the pure copper, but then it'd maybe increase again when the copper from the blister copper is oxidized. Which one of the following has the highest boiling point? So that one looks like has an ester bond. That has that has two hydrogen bonds there. Um, so that looks pretty nice. However, um, so we want to look at ones that have sort of a. So what does this look like? That's that. N H C H C H N H CH3. Okay, interesting. So this has two hydrogen bonds. However, okay. Um, yeah, so generally speaking, carboxylic acids, they form dimers much more easily when intermolecular bonding, as opposed to NHs. So even though these have two hydrogen bonds, you always want to go for your carboxylic acids. I mean, I feel like that one isn't something you can use sort of, intuition. It's more like you kind of just have to know it. Um, Also 19 here. This one also you kind of just got to know. Both have structural isomers that are not cyclic. That is true. Both have the average bond strength. No. Both are members. No. They're not part of the same homologous series. Okay, because they don't even have the same functional groups. Um, and then each carbon and the second, I'm pretty sure they actually have the same amount of valence electrons. Okay, the A. C5H10O that are aldehydes. There are three isomers. I don't think so because the only way an aldehyde actually forms is if the uh the COH is at the end, right? So that's how an aldehyde forms. So I think there'd only be two. There's one isomer with an ethyl side branch. There are two isomers that have one methyl side branch. There are two isomers that have two. Oh, there could be three isomers. Okay, each isomer has a functional group on the second. Okay, let's think about this. So we've got one, two, three, four, five. Um, it is. Okay. Mm, is there anything else we can do? I'm just gonna try it properly, actually. So that's one, and then we can do something like that's one other one, and then another one we can do is the other one we can do is this CCCOH. That's three. Okay. So an ethyl side branch, I don't think so. Um, Let me know if there's any others. Yeah. Okay. Cool. Or could there be one like here? Okay, that's four. All right. Okay, so there's definitely more than three isomers then. Um, Cool. And then you have two. There's one isomer with an ethyl side branch. I don't think so. There is an isomer with a methyl side branch. There are two isomers that have one methyl side branch each. Yes, that is true. Each isomer has a functional group on the second carbon atom. You can't guarantee that. So I'd say it's C, okay? Because we can have this one and we can also have this one. Which one of the following chlorobutyl butanoate? So we want four carbons. So one, two, three. There should have been another one there. Um, so whatever's facing the oxygen should be our alcohol. So one, two, three, four. So that should be so that's structured wrong. Or the three or should be three chlorobutyl. Okay, so it should be three chlorobutanol. So one, two, three, four, and then the chlorine is bonded to the third carbon. So whatever's facing the oxygen, that's our alcohol. And then butanol weight, so it'd be one, two, three, four. So it'd be D. Compound J. The products of this reaction are glycerol. The triglycerides, the products are, what is the, so this is just a, methyl ester. This is just so it's basically what is it? It's COCH3. That's the alcohol bit. So the fatty acid bit would be th that minus that. So because that's the ester bond, and then in that is the alcohol bit. So we need to get this part. So that would be um what is it? C18. H27. So that's the initial part. That's the fatty acid bit. And then COOH, right? Cool. So it would be C18. So it'd be, and then it'd be your C18, H27, C18, H27, C18. Okay, this is going to be pure guess, but it should be 18 times 3 plus 6 carbons. So 54. No, I've done something completely wrong here. Oh, wait. Oh, wait, sorry. 19 minus 2 carbons there. So it should be C17, H27. C17. So it'd be 17. So 17 times 3 is 51, plus 6 is 57. And then there should be 3, 6 hydrogens. So it should be that. So there'll be 1, 2, 3, 1, 2, 3. So 6 oxygens. That's tough. H2O should be added to KH directly. H2O should not be. H2O should be added to separate the triglyceride from glycerol, since the triglycerides. So it's not soluble in water. It's like what fatty acids are all about. H2O should be added to KH directly because KH is corrosive and causes skin burns. I don't think that's a consideration. H2O should not be added to the reaction mixture because it interferes with the desired reaction. Yeah, yeah, most likely. Um, why would you, so it's an esterification reaction. Why would you add water into it? Also, water is being produced, right? Technically, if you kind of think about it. Or is it? Oh no, it isn't. It isn't. It isn't. But still, you should not add water in this situation. Okay. Yeah. I think, yeah. For some reason, I remember it producing water. Just let me know if I'm wrong. Oh yeah, because it's forming an ester. So to an extent, it's a condensation reaction. If you're adding water to it, it will just interfere with the process. Um, okay. Do we have to figure out? So before H2O, 8H plus. So that's 5 electrons. So that's two, that's 5. So there's a 5-to-2 ratio. Okay. So we just have to do simple, it's actually not bad. Um, so that's 0.01 times zero point 0.1, which is 0.01 moles. And then that's going from here to there. So we times it by 5/2, which is 0.001 times 2.5, which is 0.0025 mole. And then it's asking for volume. So you got zero point 0.1 moles per liter of oxalic acid. So you just divide it by that. I am completely lost. N equals to CV, which means V equals N over C. Yep. So that divided by zero point 0.1 times by 1,000 is 25. Is 24 is D? Yeah, so 0.0025 divided by zero point 0.1. So I'm sorry I went through that pretty quickly, but pretty much speaking, okay, you are basically they've given you the half reaction. You need to figure out the molar ratio between C2H2O4 and potassium permanganate, which is that. So you just got MnO4 to Mn2 plus, which is normally now if you didn't know Mn2 plus was being produced, you can look at the data book and then you do that, you figure out there's a 5-to-2 ratio. Sorry, I should probably, if I'm actually doing a exam walkthrough, I should probably go in a bit more detail. But yeah, let me know if you need a bit more help with that. Sorry about that. It is a bit, I am a bit tired. 25. So well, basically, the highest retention time is someone that's gonna love the non-polar stationary phase. Highest retention time. So what's really so out of all of these, what's really polar non-polar? Probably your C and D, your hexane. And then what's your least polar? So out of these two, what's your most polar? Sorry. So um that has a carbonyl functional group, but this is a hydroxyl functional group. So that's hydrogen bonding and stuff like that. So that's way more polar than dipole. So it'd be D, right? If you think about between these two, which has a greater difference in electronegativities, it would be definitely this one. I mean, that's why hydrogen bonding exists in the first place. Um, so yeah, so running a series of known, yeah, under the same conditions running this. Yeah, so this is pretty stock standard. Like whenever we're creating a series of, yeah, whenever we're trying to calibrate and things like that, um, it's pretty stock standard. Presence of chlorocarbons in a compound is shown more clearly by performing volumetric analysis than by its IR spectrum. I don't think either of those actually help with showing chlorocarbons. The presence of chlorine is shown more clearly than in its mass spectrum. No, I think mass spectrum shows it much more clearly because of the isotopes. Carbon-13 NMR focuses more on carbon environments. The number of carbon-carbon double bonds is shown more clearly in its HPLC spectrum than by using an iodine test. No, iodine test is our first line test. The presence of our primary hydroxyl group is shown more clearly in its HNMR spectrum than by adding acidified potassium permanganate. That is also first line because or the thing is though, This doesn't differentiate between primary and secondary hydroxyl. This doesn't differentiate between primary and secondary hydroxyl groups well because they would both undergo oxidation and then cause a color change in the potassium permanganate. So maybe a HNMR is more effective in indicating that, but that's a bit hard. So CONH there, that's an amide. Then you've got what is that? So that's what is that? That's a carbon that's connected to OH and an OH. Okay. So we definitely have an amide, amide. I don't think we have carb. We do have, oh, do we have a carboxyl? I don't think so. No, I don't think we have a carboxyl. Do we have an amino? See, it really depends. So right now I'm leaning towards amide hydroxide, and obviously we've got our alkenols. Okay. So alkenyl. Um, so the alkenyl basically refers to the double bonds here. So be A. So there's no carboxyl and there's no amino either. So reaction between sulfur atoms in proteins. Um, I was thinking disulfide, but it contributes to the tertiary. It's the formation of covalent bonds. Yeah. So it's like the disulfide bridges. Which section of the process? So a 50 milliliter solution was placed in a conical flask. So obviously that's the method. So B or C, the average concentration is within the range claimed by the manufacturer. The table shows the titers from the titration. So this would be the results. Okay. And then that is basically discussing whether the range is true within the manufacturer. Like that was claimed by the manufacturer. So there'll be the discussion. So it'd be C. Okay. Overall, not a bad exam. I kind of rushed the end bit a little bit. Let me know if you would want let me know if you need a bit more explanation on that. Was this one correct? I think so. Um, some of this stuff was hard. I'm not gonna lie. It was one of the harder exams I've done. Like up until this point, I was pretty chilling. Anyway, let me know if you have any questions. Thanks, guys.